for the curl of B. Ampere's law just told us what the value of the curl of B was. So we're interested in the curl of B because we know that this is equal to mu 0 J. But really, the curl of B becomes the curl of the curl of A. And again, magical identity. There's an identity coming to help you for this kind of thing. There's an identity that tells you that the curl of a vector field is the gradient of the div of this vector field minus the Laplacian of that vector field. Okay, so in the notes I call this equation just curl. Okay, you'll find it, and I think once again it's just an identity that you can derive component-wise. If you remember it by heart, good for you. It might come in handy one night or something. But if you don't, it's tabulated and it's there. One little note here: we've seen the Laplacian acting on a scalar field. We now see the Laplacian acting on a vector field. Okay. However, the meaning of this is really component-wise, right? So this is a vector whose x component is the Laplacian of the x component of vector A, etc. Okay, you had a question?
Yeah, what is A? Like, well, what's the unit?
So we're going to write some better explicit expressions for it in a minute. At the moment, we really view it as the source of the field. So essentially, there's only one differential unit of length between the two. So if you measure this in Gauss or Tesla, this is really in Gauss meters or Tesla meters. Yeah. Okay. So yeah, that's the thing. Now there's a nice fact here, which is that there's a so-called gauge invariance here. And what I mean by that is that we can add the gradient of any scalar field to A without changing B. Okay, why? Because once again, the curl of a gradient is mathematically zero. So there's a whole family of related vector potentials here, differing from each other by the gradient of a scalar function. All members of this family give you the same magnetic field. Okay, so somehow it's as if there was something like metaphysical about A that floats around that we don't necessarily need, but that we can play with. And that means there's a gauge freedom. Yeah, freedom, always a good word. So gauge freedom and when you're free, you got to make choices. Usually you make a gauge choice. Okay, and we'll discuss a few of those as we go along. It's all going to become clear as we go along. So the first example we'll have of this is the so-called Coulomb gauge. And here, what we are saying is that we will choose the divergence of A to be 0. Okay? And that's a choice. If the first choice that you have does not happen to have divergence is equal to 0, then you can find a scalar function whose gradient will actually ensure that this is the case. This is proven to you in the notes. Maybe I'm not going to like spend too much time on this. Well, maybe I can spend a minute on this now. Actually, I'm going to let you read the proof of this in the notes. I think we've done enough like mathematical proofs today. Trust me, you can look at this. You can always, for any physical magnetic field that you have, find a vector potential that obeys the Coulomb gauge. Okay, that always exists. Because you can start with one that gives you the right magnetic field, and if the divergence of that thing is non-zero, there's a prescription to make it 0. And that's the thing that's in the notes. So I'll let you look at this because there's like little physical content on this. So the point is that under this gauge, the expression for the curl of A simplifies to just the Laplacian on this. So Ampere's law in the Coulomb gauge looks like this. I just have minus the Laplacian of A is equal to mu 0 J, or said otherwise, the Laplacian of my A is equal to minus mu 0 J. Okay, and as usual, this equation is local in space. So this is all evaluated at R. Okay, so that's another one of these green box equations that at least this one you should know to use. Yes, you're getting good. You're getting good. Don't want a box. We want a line. J is of course a vector. Thank you. Current density. So this is Ampere's law, and what is this equation here? You remember, or which equation do you recall when you look at this? Poisson's equation. Okay, what is this? So what did we have before? What we had before was the Laplacian of phi was equal to minus rho over epsilon 0. Okay? And this was the Poisson equation. So it related the Laplacian of a scalar potential to some driving function, some source, which was in this case the density of charges. Here, what we have is a vector form of Poisson's equation. Because I can write 3 Poisson equations here. One for AX, one for AY, one for AZ. Okay? And each will have its own source, JX, JY, or JZ. So it's the same mathematics. We've done this all before. Question? Because the Laplacian being this second order operator, it sees more than just the divergence. Divergence is part of it. So the Laplacian, right? It's the divergence of the gradient of the thing. So the B itself has a 0 divergence. But that doesn't mean that the equivalent gradient of A is divergentless. a slightly different thing. It's because you've got indices floating about and they find a way around it. Okay. So, so that's the statement here. We have Ampere's law in this form, but in complete parallel to what we did in the electrostatic case, writing the solution to the potential here by, if you want, like inverting the Laplacian, we can immediately write the solution for A by, again, doing the same inversion of the Laplacian here. And how do we do that? Well, so we just write down the answer and then verify. So what does that tell us here? It tells us that A vector at position R is the, as per Helmholtz's theorem that we saw, it's the constant. So I've got a mu 0 here, except another minus sign, mu 0 over 4 pi. And now the integral over, yeah, whatever, I mean, space, really, the whole space, theta prime, of J at R prime divided by R minus R prime, like this. Okay, and this is a I put it in kind of dark green, but maybe it's more pale green. Don't really expect you to know this one by heart, no. But I expect you to at least have seen it and recognize the parallel with the electrostatic one. So to verify, so to check or to verify this, two steps. You apply on both sides, and you use the identity that that we had, right? So the one that we used before, that the Laplacian of 1 over R minus R prime is equal to minus 4 pi delta R minus R prime. Okay, so you see, once you're happy with this this equation here, it's now automatic to transform these integral equations into differential equations for other ones. Question? Three-dimensional delta function. So that is the coincidence of the full vector in three-dimensional space. So if you used Cartesian coordinates, it would be the direct product of the x, y, and z delta functions for that point. Yeah. So Coulomb's gauge you can use whenever. Yeah, gauge. It's one of these strange English words. Must come from the Celtic or something. I don't know what it's gauge. Yeah, I will check the history of the word gauge actually. Yeah, but anyway, gauge. We will see other gauge choices later. The answer about which gauge you choose to use for a particular calculation depends on lots of things: your mood that day, your personality, your preferences, and whatnot, and whether a particular choice of gauge simplifies the particular problem on which you're working now. We're going to see later that there are gauge choices that make some aspects of the physics very transparent, some others not, when we discuss more relativistic things. No, there is a total identity between the physical properties that you derive for your things in different gauge choices. It's really a gauge invariance of the physics that's associated to this. So the representation of the physics on paper in terms of the vector potential, that is gauge choice dependent. But the physics that comes out of it, you know, the magnetic fields, which particle is going to hit this other one at which time or not, all of these things are gauge invariant. And in fact, in fact, the very notion of gauge invariance becomes super important later on, beyond this course, really, when you discuss quantum field theory, quantum electrodynamics, and whatnot, because then you've started from the statement that you want to have a gauge invariant theory. And that statement is enough to essentially codify electrodynamics. Okay? So you can view electrodynamics as featuring a gauge invariance. You can say, I'm a mathematician, I like invariances and things, and I've got these invariants and this, invariance and that, invariance and that. And here there's one invariance I call gauge invariance. And look, this wonderful theory predicts then there are things like fields, magnetic fields, and that particles have to couple to it in this particular way and whatnot. But that's the kind of much more deep way of thinking about these things, and we're not quite there. Okay. So that's the idea. And in this particular case, the Coulomb gauge allows us to immediately map to earlier calculations we've done. That's why we do this here, because we had done a lot of work for electrostatics, in which we had dealt with Poisson's equation, we had discussed uniqueness of solutions to Poisson's equation, blah, 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 blah. And now, because we are choosing this chap here, 0, therefore the Ampere law looks exactly like a kind of multi-component version of what we've already done. Yeah, that's why we've made this choice here today. Okay. But now, so remember, absolutely everything we struggled through with Green's identities and whatnot, they're all applicable here immediately, right? You don't need to redo them because you already know them. Okay. So again, here, if you were to find a solution to this equation, there's no worry that you should look for another, because you can invoke Green's first identity. You know that if you have a solution, it is the solution for that particular gauge choice and for these source currents. Okay. So that's the idea. Okay.